Okay, we're going live. Cool. So welcome everyone to the second seminar of the Research Seminars course. Today we have a very nice topic and a great speaker. Let me just admit the people that are trying to come through. For some people that may just forget, you probably need to, for the upcoming talks, you probably need to connect with your Unistart account so you don't have to wait for me to accept people in. But so as I said, everyone, welcome to the second talk of the Research Seminars course. We have Derya Akkaynak, if I said it correct, that Diego will be introducing more like lengthy in a short time. That's basically for the people that are taking the course, that are enrolled in the course. Remember, you have the questionnaire about the talk that will be open as soon as Derya stops giving the talk, and also the paper reading task. So Diego, if you just want to.
Yeah, thank you, Julio, and thank you again, Derya, for agreeing to give this talk. So this is a very cool mix of research and adventure that we hope that you enjoy. So Derya is an engineer and oceanographer. She got her PhD at MIT and the Woods Hole Oceanographic Institution, whose research focuses on problems of imaging and vision underwater. She has professional, technical, and scientific diving certification and has conducted underwater fieldwork in the Bering Sea, the Red Sea, Antarctica, Caribbean, the Northern and the Southern Pacific and Atlantic, and her native Aegean. Derya was a finalist for the 2019 Blavatnik Awards for Young Scientists for resolving a fundamental problem in underwater computer vision, a new equation specific to the reconstruction of lost colors and contrast in underwater photographs. She's starting her research lab in Iliad, if I pronounce that correctly, probably not, in Israel. What you want to know, and she will be mentioning this, is that she is on the lookout for good students. So if you want to go to Israel, if you want to dive and go to the beach and call it research, then you probably want to contact her after the talk. Anyway, Derya, thanks a lot, and all yours.
Diego, thank you for that fantastic introduction and also the invitation to talk to your colleagues and students today. I will go ahead and share my screen and hope that all of you can see it. It looks good?
Yeah.
Okay. Excellent. So thank you again for this opportunity to talk to all of you. I have a very full and diverse talk today. And as I was saying earlier, I am available to answer questions for half an hour, 45 minutes after. So if you have to leave right on time, feel free to leave, but I'll be here. So with that being said, please join me now. Oops. In a journey to explore why there are colors in the ocean. So here's how I structured today's talk. First, I'm going to tell you very briefly about myself, and then I'll tell you about some of my visual ecology projects that I'm actually not going to be talking about in detail at all. After that, I'll move on to the main topic for today, which is why are there colors in the ocean and what do colors mean? Do colors give us any kind of scientific insights? And why is color imaging in the ocean such a hard problem? Then I will summarize very briefly some of my contributions towards solving this hard problem, namely a new equation for the ocean and an algorithm that uses this new equation. So with that, very briefly about myself, I was born and raised in Turkey, and by training, I'm an aerospace engineer. When I finished my bachelor's degree, I graduated first from my university and I got a scholarship to go to MIT to do a master's also in aerospace engineering. And I finished that in 2005, and I kind of did not feel a passion for what I was doing. I was working on the thermodynamics of aircraft engines, jet engines, and wasn't all that interesting. So I said, okay, let's go see what it's like to work in the industry. So I started a job in the finance sector, but as an IT consultant. So I was doing programming for companies like banks or credit unions or loan owners or loan providers. And I did that for a few years. I made a lot of money, but then I realized, well, I'm always stuck in the office. I come in before sunrise, I leave after sunset, and some years I'm missing the changing of the seasons, and that really makes me a lesser person. I felt that I was becoming more nervous, more angry, and unpleasant person because I was missing my connection to nature. So despite all the money I was making for some 20-year-old, I asked myself, okay, what is a job that I can do that will restore my connection to the world and make me feel complete in that aspect? And the answer was a job that takes me to the ocean every day, or a job that brings the ocean into my life every day. So then, almost at the age of 30, I went back to school to get a PhD in oceanography. And I never looked back. I finished in 2014. Since then, I have been a postdoc in Panama, in Germany, in Israel, in the US. Most recently, until last Friday, I was actually working at an oceanography institute in Florida. And in a month, I'll be starting a tenure-track job as an associate professor in Israel. And with that, before we get there, since I spent 2 years in Florida, I just want to tell you a couple of cool things about Florida. So there's a lot of weird people here. That's one of the probably the most interesting things. And the second is there's a lot of weird animals. These are manatees, also known as sea cows. And this photo I took right on our campus where they come to hang out in the canal of our university. And they're mammals. And the two little ones here are actually nursing from their mothers, who has the milk gland right underneath its, I guess, elbow, if you can say elbow. And the other cool thing is you go for a random walk anywhere on the beach in Florida, and you have the opportunity to find some interesting packages. One day I was walking on the beach and I found this package you see here. And very unfortunately, it turned out to be only marijuana. It was 8 kilos of soaked marijuana. And I say unfortunately because both me and the sheriff who came to open the package were really disappointed because it has no value. There's zero street value for seawater soaked marijuana. But anyway, this is the end of my time in Florida. I have good memories. And now I am moving on to the beautiful Red Sea to start my tenure-track job. And as Diego said, I'm hiring. So if you have any interest in working on problems of imaging and vision, and that means animal vision and computer vision and optics and computational photography, specifically in the domain of aquatic habitats, underwater, and you would like to dive for your work, and you would love to live in a beautiful desert area, this could be a great opportunity. So please don't be shy to get in touch and tell me if you're interested in any way. But with all that advertising, let's get started. So what do I do? You heard that I have an aerospace engineering background, and I'm an oceanographer, and I'm also giving this computer vision seminar. So it's all a bit confusing. It's confusing to me every day as well. But my research actually bridges together ocean optics, which is essentially physics, and biology, biogeochemistry, visual ecology, which is how animals see and what their specific visual systems, how they have evolved to help their lives, to help live their lives in a certain habitat, and computer vision. But at the end of the day, I'm an oceanographer. I only care about the ocean, learning something new about the ocean. All of these fields and topics are tools for me to learn more about the ocean. I'm actually not a computer scientist. I took Computer Vision 101 from Antonio Torralba. I took Computation Photography 101 from Fredo Durand. And I don't have any other computer vision formal education behind me. So you're listening to me today as an oceanographer who uses computer vision for her research. So as promised, a very brief intro to some of my visual ecology projects, so you can see how we can combine optics and biological vision with imaging technology, hardware and software. So I'll give you two examples, one from my work with cuttlefish, the other with sea turtles. I'm gonna start by playing this video, which I'm sure all of you have seen because it's so famous. It's been all over for many years. It was taken by my PhD advisor, Dr. Roger Hanlon, when he was working in Grand Cayman in 2005. And as I play the video, I imagine you guys will see a slightly slower and perhaps lower frame rate. So you'll still, the main idea will still come across. I'll go ahead and play it now. And as you watch it, as the camera moves, just continue looking at that rock there. Just keep focusing on that rock. And soon enough, you'll see that actually it's not a rock, it's an octopus. And these animals, octopus and cuttlefish, of course, in addition to being delicious, have this incredible ability to dynamically change their appearance. Now we'll see it in reverse. So watch the area between the eyes. That's where the brain is. That's where the camouflage and the coloration starts from. Within milliseconds, they blend in with their background habitats and fool our eyes and the eyes of their predators into thinking that they're not there. But what's most impressive to me is not that they can do this in milliseconds, but they are actually colorblind. So these animals have only one photoreceptor in their eyes, which means they cannot discriminate colors. Yet they are still able to achieve this incredible look. So cuttlefish, of course, sepia, is a relative of octopus. And I've been studying these for over 10 years. This was my PhD topic in the lab and in the wild, and trying to understand what is it in the background that makes them put on that particular camouflage pattern when they can put on an infinite number of patterns. So I put them in little arenas like this, and I time-lapse them from the time I put the animal against this new background to the time it displays a stable camouflage pattern. Now, of course, as you can imagine, checkerboards, sine waves, cow patterns are not natural backgrounds, but they are backgrounds whose statistics I can precisely control. So by analyzing their behavior, and this has to be done with hundreds of backgrounds and dozens of animals, by analyzing their behavior over time and spatially, I am trying to get some insights into when they make a decision to camouflage, what are they basing it on? So this is one of the kinds of things that I work on. And also this has a field component where we go dive in the places where these animals live. We find them in their natural habitats and image them and do all kinds of image-based analysis. My other project that I wanted to show you is on the visual systems of sea turtles. So sea turtles have a fourth photoreceptor. As humans, we are trichromatic, but turtles also have a UV sensitive cone, which is really cool. But in addition to that, on their retina, on top of the photoreceptor, they have these colored oil droplets. They are yellow, orange, or red, spread all across the retina. So here's the cones, here's the photoreceptor, and at the end of it, you see the spherical oil droplet. And the role of this in an aquatic habitat is really curious, because the only other animals that have this kind of microlenses on their retina are birds. And birds, of course, live in terrestrial habitats. There's broadband light. There are a lot of colors enabled by that broadband light. And birds themselves are very colorful. So theoretical work shows that these oil droplets give birds the ability to discriminate more colors, which makes total sense because birds communicate with colors, they find mates, and they find conspecifics based on colors. There's a lot of role that colors play for birds. But no offense, turtles are not colorful. And the aquatic habitats they live in, by the way, both freshwater and ocean turtles have the same colored oil droplets. So the aquatic habitats they live in are not colorful, they're dull because of the attenuation that's going on in the water. So even if the background has color, the water takes away that color. So why do they need to have these oil droplets? And turtles have been around for 150 million years, and they've had oil droplets for 150 million years. So it must clearly be giving them an advantage. So why and what? So to answer this, we thought, okay, well, it would be really cool to see the underwater world from the perspective of a turtle. So why don't we build a camera that senses the world like a green turtle, which we did. When I was a postdoc in Tali Trebich lab back in Haifa, we took a 16-band multispectral sensor, built an entire computer, battery, peripherals around it, built the housing for it, and essentially built a turtle-like camera that was not RGB, but it was multispectral, so we could take the output and then we could project it offline to the visual system, the spectral sensitivities and acuity of a turtle. And this is the first dive of the camera that you're seeing in the Red Sea. And what this is cool, but what's even cooler is the imagery that came out of the camera. And that's here. So on the left side, you see the world, the underwater world, according to an actual turtle's visual system, which has oil droplets, as best as we could simulate. On the right-hand side, you see the same hyperspectral data cube rendered for a turtle, the same cone sensitivity, but no oil droplets. So even though I said turtles are not colorful, aquatic habitats are not colorful, blah, 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 it appears, at least from this level of analysis, without knowing on what's going on in the brain of the turtle, we see that there's quite an advantage to having these oil droplets, because already you can see there are more colors to discriminate. What does that mean for turtles? We have no idea. That's next. So that is basically the intro part of my talk, to show you what does somebody who has an aerospace background, who later turned to oceanography, do in visual ecology. Now I'll move on to the core of today's talk and start with the question, can ocean colors give us scientific insights? And I will cut to the chase. The answer is yes, of course, because the color of the water tells us something about what is in the water column. And one of the things I resent the most about computer vision work underwater is folks very commonly assume the ocean is blue and the red wavelengths are attenuated first and therefore such and such. So that is only true for the open ocean, that the ocean is blue and long wavelengths are attenuated first. Actually, we do the majority of our scientific imaging in the coastal ocean. And in the coastal ocean, the optical conditions vary dramatically. And it doesn't have to be that the long wavelengths are attenuated first. It could be that the short wavelengths are attenuated first, and you end up with a yellow habitat or a green habitat or a brown habitat. And of course, the nature and type of the particles inside the water determine how far visibility you are going to have, which also affects the animals that live there, scientists who want to do imaging there. So the dominant color, which tells us about what's in the water, and the visibility are two key components of looking at any underwater habitat. So I have here examples from top left, which is the clearest spring in Florida that I could find. And you have maybe up to 100 meters of visibility. And also at the end, a coastal lagoon from Florida, where you have maybe a few centimeters of visibility, and then everything in between. So please, let's not make the assumption that the ocean is blue and long wavelengths attenuate first, because the ocean is really big and the conditions are highly variable. But going back to what do these colors mean, and do colors give us scientific insights? I want to show you this map from 1989, because This was the first time that scientists were able to see the entire planet, the entire global ocean from a satellite. And the satellite had gone up about a couple decades before, but it took about 10 years to make this map. And what you see here in false color is the concentration of these tiny organisms called phytoplankton. So these are tiny organisms that photosynthesize in the ocean, and their concentration, when it's high or it's low, has some very significant meanings. And I'm going to come to that in a second, but I just wanted to tell you that sometimes when we start our research, we start with the state-of-the-art technology, and maybe we don't know the history so well, but it took about 10 years to make this map. And until that point, there was no confidence among science in the science world against the scientists who said, maybe if we could image the world from space, we can learn something. And everybody thought, are you crazy? You would never be able to do that. It's not possible. And all kinds of resistance to that idea. But of course, today we do that on a daily basis from satellite instruments on satellites. We do it with extreme high resolution. And this gives us all kinds of insights about what's going on in the ocean. And one of the most interesting things I will tell you as an oceanographer is being able to see the ocean from this angle revolutionized oceanography, because until this point, everything you see here is real. And until this point, when scientists went out to sea to take samples between 2 points in the huge ocean, they assumed everything between those samples, locations, varied linearly. But if you look at this, you see that there is nothing varying linearly or smoothly. There are eddies, there's turbulence, there's jets, there's all kinds of mixing going on at every spatial and temporal scale. So just being able to see the color of the ocean completely changed our understanding of oceanography. And there's a whole field called ocean color. Just to wrap up, this is a simulation. It's an update of the 1989 map I showed you, where purple colors are high concentrations of phytoplankton, and warmer colors and blue are low concentrations of phytoplankton. And it shows you globally, spatially, and over time how these might be changing. And why is this important? Because the color tells us how much plankton there is. The plankton does photosynthesis. What does that mean? Photosynthesis means food. So everything in the ocean starts by eating this food. This is the food that sustains the ocean. When you photosynthesize, when these tiny organisms photosynthesize, they use up carbon dioxide. And when you use carbon dioxide, I'm sure all of you know what this means. It tells you some important role of the ocean, of these little organisms in the Earth's climate. So it's extremely important that we understand why the ocean is the color it is, how it changes, and what it means. But for some people, and I might be one of them, the fact that the ocean water has color is a huge problem, because I don't care what's in the water. I want to see what's on the bottom, and I want to see the real colors of everything on the bottom. And I want to be able to do that at large spatial scales. But I cannot, because the water has color and it ruins everything in my photographs. So my work and my future work is all focused on overcoming this problem of the watercolor, so I can see the colors of actual ocean residents. And here I want to give you a very brief background on how an image is formed underwater. You guys know this intimately, but because it relates to the terms I will be using for the rest of my talk, I want to just take 2 minutes and walk you through it. So here's a diver, and the diver wants to take a photo of the octopus. And the image that will be formed on the sensor of this camera will actually be a superposition of 3 different images. So the first image will be formed with the signal that comes from the sun and hits the skin of the octopus, and it will scatter directly to the sensor along the line of sight, and it will not scatter off this path, and it will directly reach the sensor, and it will contain the most information about this octopus. A second layer will be light that comes from the sun that hits the octopus's skin, but then when it's traveling away from the octopus skin, it will hit these exaggerated animals, the plankton or organisms that are floating in the water column, and they will scatter in different directions, but eventually find their way back to the camera sensor. So this we call forward scatter, and it sort of degrades the image by adding a blurry version of the octopus's image that we want to take. But that's not a big problem. The real big problem is the signal that I represent with the red arrows. So these exaggerated floating particles in the water, when sunlight hits them, they scatter light towards the camera, but notice that light with the red arrows have never been to the skin of the octopus. So this layer of image, which we call the backscatter, absolutely contains no information regarding the octopus and the scene. It's just a layer of colored fog, just like fog and haze that we work with in computer vision and live in our daily lives. And this is the main degrading element of most underwater images. So the signal with the blue arrows, the direct signal, is the most valuable one. We would like to work with that. Backscatter and forward scatter are not valuable. We would like to eliminate them from our photos. And between the two, forward scatter is the least important, even though people have written entire PhD theses on that. I'm going to ignore it for the sake of today's talk, but that doesn't mean it shouldn't be worked on. So after this very brief introduction, I want to show you with a small simulated example of image formation. So here we have the diver again, but the diver is now on the bottom right of the screen. And the diver wants to take a photo of the color chart, which is right above the starfish, actually sea star. And where he is now, when he takes a photo, he's just too far. The direct signal will be almost zero because all the signal that will reach his camera will be backscatter. And remember, backscatter has no information about the scene. It's just a layer of colored fog. So his image will be all blue and there will be no sign of the color chart. Only when he gets a bit closer, the direct signal will become non-zero, but it will still be not colorful because the colors will be attenuated, and there will still be a significant amount of backscatter that clouds the image. So this is also not a very good photo. Only when the diver will be right up next to the color chart, minimizing the distance between himself and the scene, the direct signal will be almost entirely the color chart, and the backscatter signal will be almost entirely zero. So the backscatter grows exponentially with distance, and the direct signal degrades exponentially with distance. Everything happens with distance. So if you're into underwater photography, this is your most important takeaway. Get as close to your scene and your subjects as possible if you want to be able to edit your photographs in a pleasant way later. Now, this was a simulated example. I want to show you a real example. So this is a color chart, waterproof color chart. And I took this and I mounted this on a line in the middle of the water that was about 17 meters from the surface and 17 meters from the bottom. And the importance of that is we are away from reflections from the surface and reflections from the bottom. We are in blue water. So I swam to this color chart from 8 meters away, getting close to it and taking a photograph at regular intervals. So from left to right, you see here the raw image, unprocessed linear, from 8 meters all the way up to 30 centimeters. And notice how on the left images where the distance is large, there is that layer of fog, that layer of backscatter that I mentioned. There is, you can see the color chart, but it's occluded by a layer of fog. And here, I computationally calculated the amount of fog at each distance, and I subtracted that from the raw image. Now compare the second row to the first row, and you'll see how the sharpness of each photo at each distance is the same. So that layer of fog is now gone. Now, on top of this, I am going to restore the lost colors for each patch. Now, most people here get hung up on the purple background. Don't look at the purple background, just focus on the colors in the chart. And notice that from the furthest one to the closest one, colors are standardized consistently because they are corrected by taking into account the distance. So this is sort of a real world example of how we lose colors, how this color chart in air looks so colorful, and in the water, with growing distance, we lose all those colors and gain a layer of fog. So with all that being said, my main area of focus is color restoration underwater. When we are given a 2D image that looks all blue and blurry and low contrast, and somehow we are expected to get to its unattenuated version. And think about it for a second, because many of you, including Diego, Adolfo, work on simulating underwater scenes based on physical properties and real optical properties, and taking into account viewing geometry and all aspects that you need for the radiative transfer equation. On my end, I get stuck with 2D images. I don't know who took them. I don't know where they were taken, how deep they were taken, what the distance was when they were taken, what sensor was used, what angle it was taken from. I don't know anything about what's in the water. So I am stuck with some unknown 2D projection of an underwater scene according to some unknown sensor. And I am trying to restore what was lost in that projection. It is actually a very hard problem. And one of the things that drives me insane is when people come to me and say, well, isn't that just white balancing? And I was really losing it in the beginning when folks suggested this. And then I thought, okay, people don't have to know how this works, so relax. So white balancing underwater cannot work. And the reason for that is because white is different at every point in every underwater scene. So here I placed 6 color charts in increasing distances from the camera. 5 are on the floor, and the 6th one is being held by a diver. And here I extract the white patches of each of these side by side. And not only does it change with distance, but it's probably a cloudy day. So if you look at the difference between 1 and 2, even though 1 is closer and 2 is farther, 2 is brighter than 1 because there's all kinds of spatial effects. So the light is not uniform. So when it changes with distance like this, unless you have a very simplistic scene, you cannot use white balancing. There are cases where it can work, and it can work great, but in the whole of underwater imaging, especially for scientific purposes, that's a very limited scenario. So why have we not made a lot of progress in color reconstruction? Most of the algorithms up until a couple of years ago failed on 3 common modes. And the first mode of failure was the algorithm would change the colors and not really restore them. So this is one of the most common ways that existing algorithms don't work. The second way it fails is that it does a great job of removing backscatter, which means that layer of fog is removed so we can see much further into the scene, but it exaggerates that at the expense of colors. So either you have good visibility and bad colors, or the third common failure is Colors close to the camera are compensated properly, but colors away from the camera are overcompensated. And I don't know if it comes through in your screens, it may be hard, but here at about the third color chart and beyond, the red colors blow up, and also the color balance is off. But close distances are okay, far distances blow up. So why was this happening? When we, in the last 10, 15 years, we've had this incredible revolution of image-based learning and analysis for photos taken on land, why have we not been able to do this for underwater images? And to answer that, I'm going to take you guys back 200 years. Okay, so it was about 200 years ago that the first photograph was made. Not much long after, just about 30 years after the first photograph, the first underwater photograph was made. This is, of course, not by having a camera underwater, but putting the camera in a wooden room and submerging the room underwater. And just about that time, in the early 1900s, we were actually able to make very sensitive and accurate measurements of sunlight spectrum deep in the ocean, down until about 500, 600 meters. That was amazing. And after World War I, and before World War II, there was a lot of progress made in visibility in the atmosphere. Of course, World War II then brought on a new frontier, and all of that progress was also taken into the underwater domain. And once the war ended, some of this research became public, and most notably, Siebert Duntley established his research, which had been on atmospheric visibility, also on underwater visibility at the Visibility Lab at MIT, which later moved to Scripps. And then came, of course, the first underwater camera, the Calypso. And later, Duntley published his seminal paper, Light in the Sea, which we still read and cite today. It's, with the exception of some details, it's still very accurate physically. And then came, in 1975, the first digital camera. Maybe many of you didn't know it looked like this. I certainly didn't know, because that was before I was born. But nevertheless, that's a cassette tape on the side. And in that time, between 75 and 80, the first computer simulations of underwater scenes started to be performed also in the Visibility Lab at Scripps. And these simulations were given all the inputs, trying to create as realistically as possible underwater habitats on a computer. So imagine it's 1980, that's still pretty hard. Their work was then refined by Jules Jaffe. And I've given you all this background because I've been trying to get to 1999. What happened in 1999? A seminal paper by Sri Nayar and Srinivas Narasimhan was published that was called Computer Vision in Bad Weather. So now we are at the end of 90s. There are digital cameras that are available and affordable to researchers. And we have better computers, we can write algorithms. And this paper actually identifies, it takes the radiative transfer equation and simplifies it for the conditions of the atmosphere to reach a projection of light to a trichromatic camera sensor. And it does a really good job of doing that and establishes the image formation model for vision, trichromatic vision, camera vision in the atmosphere. And that's excellent. But then from that time on to 2018, that atmospheric model was used for correcting images in the atmosphere. And you can imagine there are a few problems about that, which I will talk about in detail. But in 2018, finally, we updated this and derived a new equation specific to the ocean. And this equation is actually more complex. It has more parameters than the atmospheric model. It's more difficult to solve. You need a lot more, you need to estimate a lot more parameters. but it very clearly explains why the atmospheric model had been making underwater algorithms unstable. So imagine this for a second. On the left, you have an atmospheric scene in fog, and on the right, you have a typical underwater scene. It is very clear that in the atmosphere, while the fog occludes your vision, it's still white. There isn't green or blue fog for the most part. And also, you lose visibility, but you lose it over dozens of meters, sometimes hundreds of meters. But in the underwater world, there is always a color cast, which means light is being changed as a function of wavelength, which is not happening in the atmosphere. And visibility at the maximum is just a couple of meters. So it should have never worked to use the atmospheric equation for the water, but somehow it did. And very quickly, since you guys might be working on dehazing in various aspects, I want to show what's different. Here is the atmospheric model that's very commonly used. Until a couple of years ago, it was used for vision in the water as well. And what I highlighted in green is the attenuation coefficient. What the new model has is two different coefficients, one that governs color loss and one that governs backscatter. Remember, backscatter has nothing to do with the information in the scene. So the things in the scene and the fog cannot possibly change at the same rate. And the new equation that we derived updates this. And these parameters have a bunch of dependencies that we now explicitly list. I won't get into this, but I'm happy to take questions about it later. Just to summarize, in the atmosphere, with the exception of very few cases of colored aerosols, light attenuates independent of wavelength. And in the ocean, there is never a case where light attenuates independent of wavelength. It's always a strong function of wavelength. But it's not only that. In the ocean, the reason why we cannot image everything and train networks and learn and classify everything in the ocean is because color is lost as a function of distance. That layer of fog grows as a function of distance, and even the attenuation coefficient in the RGB domain changes as a function of distance. So if you don't know distance, you cannot restore colors underwater. This is the biggest technological bottleneck in, as far as I'm concerned, in underwater imaging at this point. I have a few more things to say about this, but at the end. So using the new equation that we derived, we devised a very simple method that restores colors in underwater photographs. The method is simple, but it takes as input a distance map. So this is not always available, but because we wanted to prove the new equation and that it was more accurate for an underwater settings, we said we're going to assume distance is known and then validate all the coefficients later. So this is the first method that uses the new equation. It's not AI, it's completely physics-based. There's no training, don't ask me for the weights. And it doesn't require you to know anything about the scene, about the water body, about the sensor, anything. It just needs a range map and it works. Of course, it does not need a color chart. And I see this as a great start to use AI at the same level of performance as we have been getting on land images for underwater. So this is a really exciting time to be working in underwater imaging and optics, if I may say so myself. So I'll just show you a couple of examples that we've run through this algorithm. Here's a typical scene from the Florida Keys. And here are the colors restored. This is a scene from Indonesia, from Lembe, which is actually, this is Papua New Guinea. And it's about a 20-meter deep coral reef. I brightened the raw image just so you can see that there's something. And here is the reef without the water. This is the image when I went, why are these colors there? Why are these red and orange and yellow colors there if nobody is ever going to see them as such? This is the Red Sea, where it all started, where I did my postdoc and where I'm establishing my lab. And here's a beautiful reef where you can see all the way up to the little fish in the background. This is the murky shipping channel in Indonesia, which looks green and disgusting on the outside. But if you actually look at it without water, it's like a forest. It's like a flower garden. Of course, because the algorithm doesn't make any assumptions about what is in the water, the only assumption it makes is that the light is natural light. You can also use it on outdoor pools. And this was sent to me by someone who saw the see-through algorithm in the press and said, I train a swimming team. My daughter's in it. And here's a photo I took. And here's what you get with the see-through algorithm. And not only can you see the bathing suits pop up, but also the skin colors come out really nicely. So I'm sure some of you are thinking, well, can't we use see-through for atmospheric images as well if those two coefficients end up being equal to each other in a special case? And of course, you would be right, because the image formation model for underwater is the more complex one. Atmospheric image formation is just a simplified case of underwater image formation. So of course, if you calculate the parameters accordingly, no problem why you cannot use it for atmospheric images as well. So I'm almost done, but I want to very briefly tell you how it works. And don't expect too much because it's extremely simple. So here is the physical image formation model that it works based off of. And remember here, the I is the image that the camera takes. The Z in the equation is distance. And in all of the examples I showed you, I obtained distance using structure from motion. So we take multiple images of the scene and actually use a commercial photogrammetry software. And then we get distance, pixel-wise distance corresponding to the image. And of course, all this work is to get to J, which is the unattenuated image. So we are going to try to get from I to J. And the first step on that is to calculate backscatter. Okay, if we can calculate backscatter and we remove it, then we can leave the J term alone and deal with that. How do we calculate backscatter? If you have heard of dark channel prior, it's similar to that, but it's not exactly the same. Remember that I have the distance map. So I can find the darkest pixels in the image, and I know their distances. So I just do that, find the darkest 1 percentile of the pixels. I plot them as a function of the distances which I have. And I know from the physical model that this is supposed to behave as an exponential. So I simply fit an exponential that fits those points. And that gives me backscatter. And once I know it in 2 points, I know it for the entire image because, again, I have the distance map. So in this scene, the backscatter image looks like the one on the right, which is different shades of gray based on different distances from the camera. And remember, this has no relationship to the content of the scene. It's just fog. Okay, excellent. So now I have backscatter, I subtracted it, and I'm left with the direct signal. Now, what am I going to do to this direct signal to actually obtain the J? I have to take that exponential, put it on the other side, and try to estimate that distance, the coefficients for attenuation. So if you think about it, that exponential is nothing other than a light map, an illuminant map that changes spatially. And lucky for us, from the field of computational color constancy, there are dozens of algorithms that actually estimate spatially varying illuminant maps for both indoor and outdoor scenes. So using one of those, we can estimate a coarse map, and then knowing how the coefficient of attenuation behaves actually falls off exponentially. I can talk about it more later. We can fine tune that map, and then we put the colors back. And then there's a photo finishing step, which I'm not going to go into. So this is all there is to it. And it's very simple, but when the physical model is accurate, the algorithm itself doesn't have to be complex. And that's probably why someone like me, who's not a computer scientist, rather an engineer with general programming knowledge, could develop this, because the fundamentals are on strong physical basis. So what's next? As I told you, the big challenge is to get distance underwater. And everything I showed you is for natural light. So eventually this has to be extended to artificial light. And there's actually a lot of challenges with that. But I want to talk about two different ways we can go about estimating distance or range real-time underwater. The first is through software. So this is actually Mitsuba that Diego, Adolfo, and Roberto and Jose from Adobe are working with me to adapt into a form that we can use for animal vision or computer vision in a way that it follows the physical rules as we know in the ocean as closely as possible. And Mitsuba is a physically based renderer, but still there are assumptions in there, like the way it simulates optical properties that are optimized for the atmosphere and do not represent real underwater scenes. So we are doing this work to be able to develop a tool that simulates a given underwater scene in many, many different combinations of real world scenarios, so we can learn a lot of things, one of which is we can use this kind of simulation to estimate range. Because if you try to train a network with real world images of range, you saw how variable the ocean is. There is not enough calibrated data to do that, to represent the whole ocean. Maybe you'll do it for very clear water. Maybe you'll do it for very murky water where you live, but there is no way we are at the point where you can do it for the whole ocean. So simulation is actually, learning from simulations is a good way to go. The second way is hardware. And that's what I've been working on actually in the last couple of years. I am working on developing a LiDAR, underwater LiDAR integrated camera. And the goal here is to make the LiDAR small enough that it will couple with any consumer camera, just like you have in your iPhones. And this real-time range problem will be solved, because in underwater conditions, LiDAR can actually go about 3 more attenuation lengths than the optical signal. So here's a prototype we built. I'll just tell you very briefly. Earlier this year, we said, let's do a proof of concept experiment and see if this will even ever work. When you combine an underwater LiDAR and a camera, can you do color correction? So here you see the LiDAR on its own, you see the camera on its own, and the light is somewhere completely else. We are just testing if the data from this will be usable. I built an entire coral reef with a turtle, color charts. We have a huge testing tank in our facilities here in Florida. So we lowered this coral reef into the tank. And basically, the LiDAR was mounted on a linear drive, and it goes up and down. This is a line scanning LiDAR. It's not an imaging LiDAR. So basically, we go up and down, scan the coral reef, record the image, and go off with the strobe and do as many combinations as possible. Here's one example where we just use ambient light. Here we use ambient light plus strobes to simulate a deep sea scenario. And here's just strobes without ambient light. And because we are in a test tank, we have the ability to very precisely control the turbidity. And from top to bottom here, you see our fake coral reef in very clear water, almost like most oligotrophic coral reefs going into more turbid and more turbid, like a sandy Mediterranean Sea environment. And what I'm going to show you is very preliminary results. Here's the clear water case, the raw image. It's very dark, it's very green, but we are able to reconstruct the colors by registering the LiDAR image to the camera image just fine, even to the checkerboard in the back, which is 8.5 meters from the camera. And here's the worst case scenario, imaging from 5 meters in very high turbidity. And most of the coral reef we can get, but the checkerboard in the back, we just don't have enough signal to noise to recover that. And also we're using a very cheap sensor. So there's a lot of things to improve, but this hopefully will be one way to go in the future. So I realize I have 1 minute before the top of the hour. So that's my last slide. Why are all these colors there in the ocean? I have no idea, but I'm going to find out. And if you want to be part of the journey to help me find out and join my lab, please let me know. Thank you.
All right. Thank you very much, Derya, for the fantastic talk. Yeah, I remember the Cuttlefish talk that you guys gave in the computational photography conference where we met. That was like 8 years ago or something. Still one of the most fascinating talks that I've ever heard. And this was likewise very fascinating. And for the audience, I think this is a very good example of the overlap of different fields that you may see as different fields, but computer vision, computational imaging, computer graphics as well. She showed the ongoing collaboration with our group. So we really hope that you guys enjoyed it as much as at least I did. So thank you. If you have any questions, you can just raise your hand. And I think, Julio, you are monitoring YouTube. And also you can type here in the chat if you want. Juan Raul, just unmute the mic and yeah, go ahead, Juan.
Hi, thanks for the presentation. I think it was one of the best ones I saw in my life. So,
thank you.
So I have kind of like 2 questions, and one is kind of like informal. So, how do you? So you mentioned that you are in. So how do you enter to this like a topic, right? Because I don't see still the connection with the aeronautics.
Yes, it's an excellent question. I think I was ready to do anything that had to do with the ocean. And I come from Turkey, from the Aegean Sea. And over there, you have cuttlefish and octopus everywhere. And you go in my village just snorkeling, and you see these animals acting up in the habitat. So this was something that was really known to me since even before I was in college. And I thought to myself, well, there are people studying this. Maybe this can be a way for me to bring this research. Back then I was really idealistic, bring this research to Turkey. Now, of course, there's no chance in the political climate, but it was just something that, I knew about. And, same with you guys in Spain. I think we talked to Diego about this in Vigo. There is incredible population of cuttlefish. It's cold, it's green, but it's there. So just exposure, I would say.
Yep. Interesting. And the second one is, so you mentioned this octopus, the camouflage thing is what attract you. And then also you mentioned that the assumption is the natural light, right? So I was wondering also if you check like these phosphorescent animals that they are in the very, very deep part of the ocean, or at least like at this case, like you can have an animal that is also the light source.
So that is an excellent question. For these animals, I have not checked the fluorescence. I don't think they fluoresce, but other animals fluoresce. There's fish that fluoresce around their corneas, around their eyes, and also parts of their skin. And people think that has all kinds of functionalities. But something very cool about octopuses is they have high resolution polarization vision. And we really don't know what information it gives them other than it gives them some extra information. So polarization math is pretty complex, and I have not worked with it myself, but if you're interested, there is a world of opportunity there to see what these guys are seeing through polarization.
Okay, thank you.
Thank you.
Thanks. Any more questions? Yeah, David, go ahead.
Hi, thank you for your interesting talk. I was wondering about the you mentioned that the depth map that you got in those experiments they were obtained with the structure from motion, but then you proposed like new hardware. So I guess that structure from motion is not too accurate in underwater, or what are the problems? Like why not using structure from motion to get the depth map?
First is it, as far as I have access to, it's not real time, and to do any scene that for all the examples I show have maybe dozens to hundreds of images behind them, and to run that in my resources takes minimum of an hour for a given scene. So I don't think there, for underwater images, there is a way to do real time just yet. If there can be, that would be phenomenal. By all means, go for it. But because of the optical challenges in the water, it also, in my experience, the underwater scenes need a lot of babysitting when you're building the model and you have to clean up artifacts so the alignment is better. It takes a lot of human input. So there's also that aspect. It's like a bit of a chicken and egg problem. You align, you make it better, you align again, you make it better, and then it finally aligns like a scene in air. So those are the two main roadblocks I see. But real time is definitely the number one problem.
Okay, thank you very much. Because I'm more into a robotics part in this master, so I was wondering also using this kind of information for robot applications. Another kind of related question, more directed to the hardware part. I don't know if you know about these new event cameras that are coming up. They basically capture the difference in light.
I don't. No,
Okay.
I don't. Tell me more.
Okay, so yeah, it's a kind of cameras that are now being used in robotics a lot, and they have an incredible dynamic range, much more speed, and yeah, I was just wondering if they were used in these kind of reconstructions.
I would love to try. If you're interested, we could come up with a project to try. Are they commercial, or are they you still have to build your own? Can you buy one off the shelf?
Yeah, they are right now being getting into the market.
Okay.
I think that Sony is developing new cameras, and yeah, there are other spin-offs that are also building them. But they are being used in robotics, so they are quite interesting.
Definitely. I'd love to hear more. So maybe we can touch base afterwards by email and see what
sure.
the applications
I'm not
may be.
I'm not an expert myself, I must say, but that's why I'm interested in knowing more about them also.
No worries. I didn't even know. So you are more expert than I am. Thank you.
Okay. Thank you very much.
Thanks, David. Any more questions? I have one in the meantime. It's a very small question, but I was missing. So, of course, I do not doubt your recoloring results, but since you have the ground truth when you lower that probably artificial coral, did you compare with the dry colors and then what you recovered?
So that's an excellent question. And as you said, the only part in the image where we can do that is where the color chart is, because we don't have any ground truth for anything else in the scene. So either we need to go into full calibrated multispectral imaging, or we have to put more color charts. For the parts where I have put the color charts, we have very good accuracy until you are so deep that the light spectrum wasn't broadband enough. So part of the light, like reds, weren't captured. And in that case, I cannot put them back. So that's not accurate. Let's say you are shallow, it's clear water, lots of sunlight, yes. But that's actually a future question for anybody who's interested. When you record images so deep that parts of the spectrum are gone, the light is so monochromatic, how do you hallucinate the colors that should have been there?
That actually ties up nicely with my next question, which had to do with same context, but now very different waters. You know, some look very green, some very yellow because of the phytoplankton and everything. Does your algorithm stay robust to changes, or yeah?
Yes, it does. What changes? So generally, when you have more yellows, greens, and browns, it also means the particles are generally bigger, so the visibility is lost faster. And in those cases, the range that I can correct gets shorter. So if you give me a beautiful scene in clear water, up to 10 meters, I can probably correct all of it. If you give me a scene in murky water in 10 meters, I can probably correct only the first meter. And then there's no signal. So color-wise, I can if the signal is there.
Right, I see. Yeah, thank you.
Yeah.
Julio, do you have anything? Okay, we have Juan again. Yeah, Juan, go ahead.
Hi again. So I have maybe like a silly question, but when you were showing this, so you showed that there was an equation, and then you like improved this equation, like making the coefficients especially variant.
Yeah.
I was wondering about the wavelength there. So like.
Yes, I will go there now.
So yes, like which are the assumptions there with the wavelength?
So this is already in, so the top equation is the atmospheric equation and the bottom is the ocean equation. Both of them are already in the domain of the camera. So the C, you see I sub C, J sub C, B sub C. Mm-hmm. The C is the color channel. So we only write this for the RGB channels. The wavelength, so there is a version of this equation one step before we project it to the RGB sensor. And in that equation, everything is a function of wavelength where you can see. So in this one, your observation is 100% correct. There is no wavelength because it's already RGB. One level before, which is in my paper, I can send you, we have the wavelength.
Well, okay. Thank you.
I'm sorry, I was muted. I'm gonna jump with another question. So I guess all the backscattering, forward scattering, and direct light, and the color twist that the sea does or the water does is dependent on the composition of the water that everything is sunk in. Can you like, my first question is, can you account for do you account for that composition parameters on your models? And then if yes or if not, I mean, depends, could you predict those compositions or those elements on the water based on your measurements of the colors that can you predict, let's say, invert what are the elements in the water, the phytoplankton or whatever elements in the water that change the colors? Could you predict them using your measurements from these images based on the improved model?
So that's an excellent question. First of all, let me say that folks who do remote sensing in that field called ocean color, that's what they're trying to do, not with RGB, but a few more bands from space. Can we do that with our image formation model? Not the way it is, because think again, there is this very complex 3D scene that we see as just a projection of, okay. And it's a projection according to the broadband curves of a camera. So going back from that into the original signal and the optical properties is really, really ill-formed. And honestly, you have to know the sensor of the camera, you have to know the distance, you have to know the viewing geometry, you have to know the depth. Right now, I can do this correction without knowing any of those. And it just seems like somewhat of a nightmare to have to estimate all of those to get the optical properties. I mean, it can be done if you know a lot of other things, but it's just really hard to get those parameters.
Okay.
So practically no. Theoretically yes, practically no.
Okay, and if
But-
you have like a more complex information on the image that you get, because we're used to time of flight cameras or transient cameras, let's say.
Yes, actually, I was about to say, if you just take a LiDAR sensor, and for what I showed, we use 532, but let's say you just use 3 different wavelengths, by inverting those, you can get the optical properties, because then you know exactly what your sensor is, what the light you're sending is, you have, you know, the exact attenuation lengths, and if you just do it for 3 wavelengths, you can get it from LiDAR. With optical camera, you know, RGB cameras, just really, really difficult.
Yeah. And maybe the combination of those or something like that, because you know, like the
Yes.
limitation on the wavelengths that the time of flight camera can get, and then you can combine it like the same with somehow the Kinect does, right? You have like a high resolution image in RGB, and then you get temporal information on the
Exactly.
sensor, on the time of flight sensor. Okay.
Exactly. And actually, while the optical signal attenuates a lot, in many imaging scenarios, like people studying reefs, sponge reefs, coral reefs, or seagrass beds, they are imaging up close. So there is attenuation, but if you're maybe within a meter, there's still a lot you can do, even with, if you even actively project light of different wavelengths that with the sunlight would have been attenuated. So there's still a lot of potential for close-up imaging. It's just a general imaging. There's no way you can use all the optical signal to restore the colors and invert the properties. Just really hard.
Great. Yeah, like I think thank you for that, and
Yeah.
thank you for the talk. That was super, like, smoothly going through all the you know the technique and all the physics. That was really nice. Thank you.
Happy to do that. Thank you.
Nestor.
Nice talk.
Hi, I have a question about the terrestrial eye camera. So you mentioned that they perceive also ultraviolet light, right? So are you also capturing that, or just the oil droplets?
That is an excellent question. So the sensor we are using in that, and at this point, it's like a 5-6-year-old sensor. It's a snapshot mosaic sensor from a company in Belgium called IMEC. And that sensor only goes down to, I think, 420 or 30 nanometers. So that sensor does not capture ultraviolet. So all our turtle imaging with that camera has been at depths where the ultraviolet already attenuated. So we are actually not able to simulate a tetrachromatic turtle. We are just simulating a trichromatic turtle in blue water. That's a very good question. Actually, it's very difficult to find a snapshot, you know, not a push broom sensor that senses also in the UV. There's a lot of application for it in ecology, especially with birds and insects, but you can only get benchtop sensors. So if anybody's interested in hardware, there is a small market for it to have a sensor with UV. Excellent question. Nestor, what are your plans after? Are you looking for a postdoc or something?
Well, we will see.
Okay, you guys have my
I
email.
have another question on this topic. So if you had that information, wouldn't it also be difficult to reproject that into RGB, or how would you visualize it afterwards?
So we would probably either do a false coloring or do it in slices. So you're saying if we had a tetrachromatic scene, right? Yeah, we would have to project it or false color it or find some other projection. Yes, we have no idea how the world looks like that.
Okay.
Again, also a very good question.
Thanks.
Yeah. Remember, this is just a master's course, Derya. So yeah.
Wow, you got excellent students, Diego. I'm delighted to get these questions.
Yeah, I have absolutely zero credit for that. So anyway, any more questions? Again, I think it's interesting. Now you heard this talk very early in the program this year. But as you progress in computer graphics and vision and computational imaging, hopefully you will see how the three fields help each other, right? And you will understand what Derya is trying to do, and how we, for instance, Adolfo, myself, and other people from the group are helping from a computer graphics aspect. If there are no more questions, I think we can call it a day. So last chance, Julio, anybody in YouTube? Anybody want to raise their hand?
I think there's not that many people in YouTube. So
Okay.
Okay.
So I'm just going to ask you, Derya, to please stick around. I want to talk to you for a couple more minutes.
Sure.
And thank you, everybody. Julio, if you kill the call, do we just all disappear?
I don't know. So
okay, we'll try. Derya, so can you stick around for a couple minutes, Julio?
Absolutely.
Yeah, sure.
Absolutely.
Yeah, both. Yeah, thanks.
Okay. Thank you, everyone.
Thank you, guys.
Thank you, everyone.
Thank
you.
Excellent talk.
Thank you for the talk.
Thank you. Bye.
Bye.